So do you usually do a break or not? What's the...
Yeah, it's pretty long session. So we were usually breaking where there's a natural pause or 45 minutes in, whatever you prefer.
Okay.
Yeah, and then you can see the question that are asked on the question and answer chat. So if you want, I can just read them to you, or if you like, for example, to have a look, you can have. And you can decide whether answer to them at a certain point or answer to them as soon as they're asked. It's up to you.
Yeah, no problem.
Okay, it's 9, but I will wait a couple of minutes to let the late people to join, and then we can start.
Okay, no problem.
Okay, I think we can start. So, good morning to everyone. This is the last day of the school. I understand that all of you may be a bit tired as the program was really dense, but I encourage you to do a last effort because today is also a very interesting day. In fact, in the last days, we saw how difficult it is to build a quantum computer and which incredible progresses were there, thanks also to brilliant minds like those of the speaker that we heard. Today, instead, we will finally see what we can do with a quantum computer that we know. So let me introduce the first speaker. First speaker is Professor Carleo. Professor Giuseppe Carleo obtained a PhD in condensed matter theory from the International School of Advanced Studies, that is the SISSA in Trieste, in 2011. After that, he works as a postdoc at the Institut d'Optique in France and then at ETH in Zurich. And in the last years, finally, as staff research scientist and project leader at the Flatiron Institute in New York City. He's best known for having shaped the field of machine learning methods for many-body quantum phenomena, and recently he has joined EPFL as an assistant professor, leading a research group focused on computational quantum science. I would like to thank him publicly for his important support to our school. In fact, he's not only teaching the next lecture about variational quantum algorithms, but he also accepted to be posted judge, and he will talk in the second part of the morning about his research in quantum algorithms. So thank you very much, Giuseppe, and I leave you the floor.
Thank you. Thank you very much for the introduction, for of course for all your organization efforts in the school. It's been really great so far. So let me try to start sharing my screen. Okay. Okay. So I assume that now you can see my iPad. So today I will discuss a quite relevant topic for current and future or near future, if you want, quantum computers, which are the so-called hybrid quantum algorithms. And to a large extent, I mean, as I will show you, or at least what I will concentrate largely on today, are what are called variational quantum algorithms. So I will tell you more about what this means and what they are about. But these things are called hybrid because they involve somehow a collaboration, a strong collaboration, if you want, in between typically small, noisy quantum circuits, quantum computers, and powerful and error-corrected, if you want, or very precise classical computers. Okay, so this is strong. That's why it's called hybrid, because we use both classical and quantum computer to get the best out of our simulations. Today I will cover as much ground as possible. We'll see also depending on the time. But I encourage you to have a look at this review here, which is pretty recent actually, as most of the field, which is moving very fast. It's from 2021, it's from this year, from January. Again, I will not typically put all the references during my presentation, but I really encourage you to look at the original references if you want. I put some pointers, but just look at the references and the original papers in this review, where you can find also more material, of course, than I can cover today. Okay, well then let's get started. Of course, let me also tell you that you are very welcome to ask questions at any point during my lecture. Just type them or you raise your hand or whatever you are used to do during these sessions. So the first thing that I was mentioning before was this variational idea, right? So these variational approaches. So what are these variational approaches? Well, it's what I would call actually a variational mindset, right? Rather than just a series of algorithms. I think that when you start thinking in a variational way, then this goes a long way. So it's not limited to run some restricted applications, but it's a pretty wide concept. So what do I mean by that? So for example, you know that in physics, there are, in classical physics, for example, there are two ways of looking at classical mechanics, right? So there's the standard way, if you want. So the Newton approach, right, to classical mechanics. So F equal ma, roughly speaking, which is, very old and very well established, and that's where you, for example, if you wanted to solve the trajectory of a particles, you would integrate this differential equation in time and find, the trajectory of your favorite particle. However, as you know, there is an alternative and completely equivalent actually approach to Newton's, which is the variational method in classical mechanics, right? So, and the idea here, and we will see that this idea again is very general, that instead of solving directly, if you want, this equation, you write a variational formulation of this equation that you can also solve with other, in some cases, even more powerful methods than for the original problem. So, for example, you know that in this case, you can define an action, right, that will depend on the coordinates, on the generalized coordinates of your particles, which will be the integral, let's say, in between two time points in time of the Lagrangian of your system. That depends on Q bar, Q point, and T. And then you know that you can get all the, if you want, you can get all the trajectories that describe your physical system by minimizing the action. So by finding the extreme points of the action, right? So, and this is, again, a very powerful idea because we've transformed, if you want, an original the original differential equation problem into the problem of looking, if you want, through all the possible trajectories, again, connecting 2 points, for example, and pick only those that satisfy, if you want, this least principal action, right? So this is the core of the variational method in classical mechanics. So we transform this differential equation into the problem of optimizing, if you want, the action. And this is, if you want, a much more, much broader approach to things than what you might expect. So it's not only limited to physics, actually. And I would argue that this variational mindset actually it's strongly permeates all modern computational science and all approaches to if you want, to devising and also doing algorithms, both classically and in the quantum world, as we will see today. So, for example, let me give you an example of, if you want, a variational algorithm. So this is a very simple example, just to give you an idea of how these things work. So imagine that you wanted, for example, you have a string of numbers, let's say a list of numbers, 6, 5, 6, just let me 6, 4, 5, 2. So this is an unsorted list of numbers. Why not? I'm given an unsorted list of numbers, and I want to devise an approach, a numerical approach, an algorithm that allows me to sort this list of numbers, right? I'm pretty sure that when you were doing your undergraduate studies, you saw a lot of these approaches like quicksort, bubble sort, etc. during your computational courses, right? So there are many approaches that have been devised traditionally if you want to solve this approach. And indeed, I mean, what you're interested in is to find the ordered sequence of this tree, right? 2, 4, 5, 6 in this case. This is all fine. However, there's an alternative way, if you want, a variational way of looking at this problem, which is the following. So let's consider all the family of all the possible algorithms. So these are, if you want, all possible algorithms that take as an input this string and that we return as an output, I don't know, my sorted string, hopefully. Okay. So then, what does it mean to have a variational mindset in this context? It means that I can define, so the equivalent, if you want, of my action would be some loss function, okay, some that I would call L, that will independ general on the specific algorithms that I've picked. Okay, so for example, I can pick a loss function that checks the output of my approach, so of some algorithm that I've devised, and counts how many times, for example, the number in the string that has been supposedly sorted are unsorted. Okay, so for example, if I have an approach, so the loss function, let's say, of an approach of an algorithm that does nothing on this string. Okay, so as you can see here, if you do nothing to this string, you see that 6 is larger than 4, so I have one mistake, one error. and also 4 is smaller than 5. So it's 5, but 5 is larger than 2. So I have 2 mistakes. So my loss function, so which is called in the jargon, if you want, of machine learning, is equal to 2 in this case. So if my algorithm does nothing, my loss is equal to 2. Okay. However, if I have an approach like where my algorithm, if you want, swaps, in this case, the first and the last entry, okay? So you see that if I swap 6 and 2, I get my ordered sequence actually. Then you see that my loss is equal to 0, okay? And there will be many other algorithms, if you want, that have a loss, so you have an action, if you want, that is minimum, and in this case is equal to 0. Okay? So if you want, the variational mindset in this context of computer science, or in general in devising algorithms, is to have a loss function that tells you how well your task has been executed. In this case, a simple task, but there will be much more complex ones we'll study. And then what you do is that you pick essentially the optimal, if you want, algorithms as a point, an extremal point in a minimization procedure. So we have the argmin, if you want, in mathematical jargon, of the loss function over all the possible algorithms. So you see, this is a very different mindset than the original way of thinking at devising an algorithm. So here I just loop, if you want. I try to explore all the possible algorithms, and I try to find the best one just looking at how well they solve a given task. Okay? So this is, if you want, the extension of the variational method also to computer science. And this is very powerful, and it is, for example, at the heart of in the classical setting, this is at the heart, for example, of many machine learning approaches. Essentially, that's what you do in machine learning. You have a loss and you optimize it. But also, as we will see, it's at the heart of these hybrid quantum algorithms that run on let's say, near-term or, but I would argue also on long-term and error-corrected quantum algorithms. Okay. Okay, now let's, of course, I mean, one thing that has to be said, in order to effectively do this procedure, so in order to effectively find, if you want, an optimal algorithm, you have to be able to parameterize in somehow this family of algorithms. So you have to be able to explore this universe of all possible approaches efficiently. So that's what you do, for example, in machine learning using neural networks. And that's what we will do in the context, instead of quantum approaches, using some quantum circuit that have been parameterized in order to solve a certain task. Okay, so this is the core of what I'm going to tell you now. So what we do then in the context of quantum approaches is essentially to solve a key task in all quantum algorithms, which is the task of performing variational state preparation. Okay. So variational state preparation means that I would like to have my quantum circuit output a certain state, so prepare, if you want, a certain state that, if you want, is the solution of a certain algorithmic task that we have defined. I will give you some specific examples on the way about some specific tasks. But in general, again, I want to prepare a given quantum state. And this family of approaches, this family of variational quantum algorithms, what they do is that they typically, this is not the only possibility, but they typically work with 3 ingredients. So the first ingredient is a way, if you want, to parameterize the states that you are preparing on a quantum machine, and this is done using typically parameterized quantum circuits. Okay. That are sometimes improperly called, I would say, quantum neural networks, but you should try to avoid this kind of naming. These are just parameterized quantum circuits. So the idea is that you have a lot of parameters that I will call theta in general. So let's say theta 1, up to theta L. So these in my presentation will be real valued parameters. Okay, so these are just parameters. What you do is that you construct a unitary, okay, u of theta, so that will depend parametrically, that's why these things are called parameterized circuits, on these thetas, and that you typically take in the form of a product of unitaries, typically local unitaries that you can implement efficiently on a computer, that depend on these parameters. So for example, you can have u1 that will depend on parameter theta 1, so which will be the first unitary you apply, u2 of theta 2, okay, up to your last unitary ul of theta L. Okay, so you can imagine, and I will give you specific examples in the following, but one simple idea just to clarify is that, for example, this u1 might be a spin rotation along the x direction, for example, and theta 1 is the angle of this rotation. So this is a free parameter that you can choose, and depending on the choice of the different parameters, you will prepare, if you want, a family, okay, of states psi of theta that will depend on all this choice of parameters that are written as typically as the application of this parameterized unitary on the 0 state. Okay, so this is a typical setting that we will be working on. So this is the first requirement. So this is the parameterized quantum circuit that will allow us to if you want, access a huge number, possibly a very large number of states in Hilbert space that I'm interested in. Okay. Now the second ingredient that we will need in this family of approaches is again a loss function. So the equivalent of the action, the equivalent of this sorting loss that I was introducing before. So in most applications, not in all of them, and I will tell you some exceptions in the following, but in most applications, so this loss function, again, this is called loss in a jargon that comes from machine learning because you want to minimize your loss. So typically that's what you do, right? And the loss function that we typically take, again, not in all applications, will be something that depends, of course, on my parameters theta, and that can be written typically as the expectation value over my circuit, psi of theta, so on my variational state, of some Hermitian operator that I call here B, okay? So, I mean, we can just also rewrite it more explicitly, but this is just, if you want the action of your unitary, your operator B, your unitary theta, and then 0. Okay? So typically, I will consider some of the loss functions of this form. There will be exceptions that we will discuss in the following, and typically, I will be interested in minimizing this kind of loss. Okay? Then the third and very important ingredient also in this story that makes actually these algorithms a hybrid is the fact that you need some optimizer, so some classical optimizer if you want to minimize this loss. Okay, so you need the classical optimizer that will allow you to find the optimal, if you want, the theta bar parameters that minimize, for example, over all the possible thetas, your loss function that depends on theta. Okay, so and typically you see the role of the classical computer is to fetch as much as possible information from the quantum computer. For example, from evaluations of the loss function that you do on the quantum computer, of its gradients, as I will show, and possibly also other information that you are able to access efficiently only if you have a quantum computer. But then using this information, you feed this information into the classical approach, and then you feed back the updated, if you want, parameters. These are typically iterative approaches, and then you rerun, you propose a new set of parameters until you converge to a minimum of the loss. So I will give you more details about this in the following discussions. But let's analyze, if you want, one by one all these three ingredients. And I think it's important, it's fruitful if we start with the choice of the loss function, which actually it's a very important ingredient when we start talking about what kind of problems, of useful problems we can solve on a quantum computer. So let's talk about loss functions. So the first ingredient that I was describing in my list, if you want, of ingredients of these hybrid approaches. I will give you some examples of loss functions. So I think that the most natural, if you want, or the easiest to understand, in a sense, loss function that we have, it's when we try to solve a very important problem in physics, in chemistry, which is the problem of preparing the ground state, right? So I have a given Hamiltonian, and I want to prepare the ground state of this Hamiltonian. Ground state preparation is the problem that I would like to solve. Okay. So I imagine that that I'm given a certain Hamiltonian H. That could be the Hamiltonian of my favorite molecule, or my favorite Hubbard model, or my favorite spin model, whatever you like. Okay? Then it's clear that in this case, the best or the most natural loss function is just the energy of this Hamiltonian over these parameter states, right? So if I just define, for example, the expectation value of the Hamiltonian H over my variational state, so you see that this is a very natural loss function, because we know from the variational theorems of quantum mechanics, so I'm not going to show that because I'm sure you already know about it, but we know from the variational theorem that this quantity is strictly equal, larger or equal than the exact, right? So this is the exact ground state energy of my Hamiltonian H. Okay, so this means that if I define as a loss this expectation value of the Hamiltonian, I minimize it, then I will find a circuit, I will find a quantum algorithm, if you want, that solves this task of preparing the ground state in the best possible way, compatibly with the constraints that I've given to the, for example, to the circuit that I'm using. Okay? So this is a typical loss function. Then the most important thing that you have to ask, for example, when you devise your own variational approach in this arena, is whether the loss function you have defined is actually efficiently computable on a quantum computer. Okay? So there are innumerable papers and discussions in literature where this is not the case. So one can typically be tempted to write a beautiful loss function that is extremely, relevant to the problem you want to solve, but then you realize that this is not efficiently measurable on a quantum computer. So the most important thing that you have to ask when you devise a loss function is whether this loss function is actually measurable efficiently on a quantum computer. For the Hamiltonian, for physical Hamiltonian, this is the case. So we can measure this loss function efficiently. So the reason is very easy. So for example, if you have a Hamiltonian H, which is a k-local, so in the sense of quantum information. So k-local means that it's the sum of only operators involving at most k bodies in the language of physics, if you want, or chemistry. But in practice, one common choice is to take the Hamiltonian to be the sum with some real coefficient ck of a string of Pauli operators. Okay. So for example, I can take, so imagine that I have n qubits, okay? And then I have one Pauli operator that acts on each of these qubits, okay? So where here I've defined essentially Ck to be a real constant. It's just, if you want, a coefficient that enters in this Hamiltonian. And then where I've defined these other coefficients, if you want, A, okay? So A, if you want, Ki, which can take all the possible values essentially in one, which will give you, in zero, that will give you the identity, if you want, or in X, Y, or Z, okay? So this is just, a slightly complicated way of saying that my Hamiltonian is the sum of a product of Pauli operators. So this can be a sigma X, a sigma Y, a sigma Z, or the identity acting on qubit 1, and the same for all the other qubits, okay? So, and typically for the Hamiltonian that are k-local, it happens that the number of terms that are different from the identity are only k, where k is this locality, it's not this index. Okay? So for this family of Hamiltonian, which is very general actually, so let me give you an example. For example, the transverse field Ising model. I mean, I'm sure that you are familiar with this example. It's a Hamiltonian that we find all the time in condensed matter, but essentially your Hamiltonian is the classical, if you want, Ising model. So you would have interactions Ij on a given lattice with some interaction coupling Jij with sigma Iz. Sigma Jz. So this is the classical, if you want, Ising model on some lattice. Okay, and then you introduce a quantum coupling, which is this sigma x term. Okay, so this is, if you want, the quantum part. And you see immediately that this Hamiltonian is exactly in the formula that the more general formula that I introduced here, because you can see that I can easily divide these terms into essentially two body terms where the locality is equal to 2, where but for 2 qubits, all the others are the identity. And I also have one, if you want, one local terms where instead all the terms are the identity but 1 qubit. Okay? So this is just to give you an example that this family of Hamiltonians is not crazy. It's actually a very general one. Okay, so but when you are in this situation, then it's very easy to measure the Hamiltonian efficiently on a quantum computer, because, for example, let's say that you were interested in measuring the expectation value of some operator sigma k of x. Okay, so k now is 1 qubit. I want to measure the expectation value of sigma k because it's one of the terms that enter the Hamiltonian. Okay. So how do I do that? Well, the idea is actually pretty straightforward, is that you use the fact that you can perform arbitrary local unitaries on a quantum computer. So the idea is that you will act with a Hadamard gate actually on my qubit k, and then you will transform, if you want, the sigma z operator on that qubit k into a sigma x operator. Okay. So if you want, what I've done is that I've done a basis rotation here in order to transform sigma x, which is in general off diagonal. I mean, I cannot measure it directly in my computational basis using just, if you want, measurements from my quantum computer, into something that instead is diagonal in the sigma z computational basis by definition. And the trick is just to apply, if you want, the basis transformation on this qubit gate. So this is the Hadamard gate that I'm pretty sure you've seen already during these lectures. But I mean, just to give you a quick reminder, the Hadamard gate is this simple basis transformation, this local gate here that is given by 1 over the square root of 2 of 1. Okay. So if you want pictorially, then if you want to measure the expectation value of sigma x, what you would do on a parameterized quantum circuit is that you would just, again, start with your input state, which is at 0. You would apply your unitary, u of theta, that will depend, again, on a lot of other smaller unitaries. And then on each of these qubits, you would apply, if you want, the Hadamard, and then you measure, as always, right, in the computational basis, each of these qubits. Okay, so you see that in this case, then the expectation value, if you want, of sigma, let's say sigma k, I don't know, of x, will be given essentially as I don't know, 1 over the number of shots, the number of measurements you've taken from the, would be estimated by a simple mean of how many times, for example, I have observed 1 minus how many times I've observed 0, let's say, on this qubit here. Okay, so this would be, I don't know, the sum over the number of shots of delta I don't know, let's say OI greater than 0 minus delta of OI equal to 0, okay? This is just, I mean, a complicated way of writing that if I observe 0 on here, I will register a -1 or a +1. This is essentially what you have, and then you know from the laws of statistics essentially that the error on the mean, if you want, of this estimator, okay, will scale like 1 over the square root of the number of samples. So this is efficient then in the statistical sense. It is efficient in the statistical sense to measure the expectation value of an arbitrary local operator, because you can just increase the number of shots. So you can just increase the number of times you run the circuit and you measure the qubits in order to have an improved accuracy on the specific observable that you want to measure in your Hamiltonian. So this is in principle, again, efficient because it's a polynomially, if you want, bounded number of samples that you would need, okay, to reach a given epsilon accuracy. Okay, so we are happy. We have a specific loss function we can in principle measure also efficiently. Now, this was one case of an important loss function, which is useful to find the ground state of a quantum Hamiltonian. However, there is another important class of problems, which are classical optimization problems. Which are actually a subset, if you want, of quantum ground state problems, but they have their own interest beyond, if you want, physics or chemistry. For example, what one can attempt to solve with a near-term quantum computer are what are called combinatorial optimization problems, right? So these typically are problems that are defined on a discrete set of variables, and you try to find the minimum of this cost function using, using some either classical approach or, in our case, a quantum approach. But the idea is that typically it turns out that essentially all combinatorial optimization problems that you have in the classical setting can be mapped onto a Hamiltonian, onto a physical Hamiltonian. So, for example, you can show that essentially all combinatorial optimization problems can be mapped into the classical Ising model, where you have, in this case, a longitudinal field Hi on each qubit, plus, again, this interaction term Vij, sigma Iz, sigma Jz, okay? Where essentially these fields and these interaction terms will be problem dependent. So this means that if I have a complicated combinatorial optimization problem, let's say the traveling salesman or any other problem, for example, a problem that I wanted to tell you about is number partitioning. Which is in NP. So it's an NP problem. It's hard to solve in general, both with classical and quantum computing, actually. And the problem goes as follows. So imagine that I have a collection of numbers, okay? So let's call these real and positive numbers A1, A2, okay, up to AN. So these are real numbers, okay? These are positive numbers. Now, my task, if you want, the problem that I would like to solve is to find a partition, so to find an algorithm. Again, this is why these things are general, that takes somehow a part of these numbers, okay, and assigns them to, for example, to a partition, the partition A, or the partition B. So what do you mean? What this algorithm might do, for example, is to put A1, A4, and A6 here, and A2, A3, and A5 in this other partition. Okay, and the goal is to do this division, this partition, in a way that is as fair as possible. So you want that the sum of these numbers that are given to A, party A, is as close as possible to the number that you are giving to part B. So you see, this is a very important problem in a lot of practical applications that go from routing to optimization problems that arise in engineering applications. And it turns out that you can rewrite it with a loss function, which is just an energy, if you want, that will depend on the, in this case, on the choice of if I put these numbers in A or B. So the idea is that I do a mapping where sigma z of I being +1 means that the number I has been assigned to partition A. Whereas if I pick a string, if you want, of spins where sigma I is equal to -1, it means that my spins, my numbers have been assigned to partition B. Okay, so if I manage then to find the minimum of a cost function, if you want, of an energy that depends on all the spins, which is the difference, if you want, between all the numbers that belong to A, right? So they belong to partition A minus all the numbers that belong to partition B. Okay, so you see that this quantity will be a minimum only if I give I give to these two parties the same, if you want, or as close as possible, the same amount of resources. So you see, this can be written as an energy because essentially this is just, you can rewrite it using this spin language as the modulus of sum of I of AI on all the spins now of AI sigma IZ. Okay, so this is using again this fact that when A belongs to B, it means that the spin is down, for example. Okay, and then it's a very simple matter of rewriting. You can show that this is also equivalent to looking to the minimum of this classical, if you want, another classical energy, which takes exactly the form of an Ising model. So essentially, instead of taking the modulus here, we take the square. So this means that in any case, the minimum will be the same. But if you take the square, then you see immediately that this takes the form of a classical Ising model. Okay, where now my couplings, again, as I was telling you before, my couplings Vij are just given by the product of these numbers. So again, you can take this very specific hard classical problem and you can try to solve it using a quantum computer, using as a cost function, as a Hamiltonian, this classical Hamiltonian. So this is a task that, for example, is done a lot in applications such as QAOA and other uses where you try to use, again, a quantum computer to minimize a classical cost function. Okay? So I realize now that I forgot to mention, but this approach where we prepare the ground state of a given Hamiltonian is known in literature, so it's important that you know also this, is known in literature as a VQE. So variational quantum eigensolver. So it's a fancy way of saying that we are using a variational approach to prepare an approximate eigenstate of a given Hamiltonian. Okay, so this is in general what people call VQE. Then in the context, when you consider a classical Hamiltonian with maybe a specific choice of the answers that I will tell you afterwards, but in general, so you can also solve these classical optimization problems or try to solve them variationally, and there are approaches such as QAOA that for example, do this. Okay? So this is another application. Let me give you yet another application, which are about excited states. Now we go back to if you want, to chemistry or physics. So again, I'm given a Hamiltonian, but now I don't want to find just the ground state. I want to find, for example, one excited state, right? So let's say that before I was interested in finding the lowest state is 0. Now I would like to find the lowest state, let's say E1, that's the energy, the lowest energy, but it is not the ground state of my Hamiltonian. So there are several ways of doing this, and I would argue that there is not, you know, a very satisfactory approach at the moment, and this is a matter of research, I would say. But one way of doing it, which is not necessarily the most efficient but straightforward, is that you do this in 2 steps. So the first step is that you first find an approximation for the ground state using the VQE approach that I was describing before. So you find some optimal, let's say, parameters that minimize the energy, okay, in such a way that this approximates as close as possible if you want the ground state of this Hamiltonian, okay? So I run the previous VQE approach and I find an approximation of my gradient, of my ground state. Then what I can do is that I can define a loss function that I will call E1 that will depend now on some other parameters, theta, that again I can define on another quantum circuit if you want, on another sort of VQE approach, and also on a Lagrange multiplier that I define here to be lambda. So the idea is that here what I will do is that I will try to minimize again the energy, so again the expectation value of the Hamiltonian, over this state, but then by using you know, the well-known method of Lagrange multiplier, I will impose the constraint that the state that I'm trying to prepare, okay, so this psi theta that I'm trying to prepare, must be orthogonal to the state that I've already prepared, okay? Because you know, I mean, this is clear that for the exact states, we expect that they are orthogonal, okay? So we expect that psi0 and psi1 have overlap 0. So I will add a Lagrange multiplier in my cost function that will essentially enforce this orthogonality condition. So essentially I will have my state that I've already prepared before with my VQE, and I will have the overlap with the state that I'm preparing now. So U of theta applied on my 0 state, initial state, okay? So you see now that if you do this constraint minimization, the extremal point of this cost function will minimize the energy and will also be guaranteed, because lambda is a Lagrange multiplier, to be orthogonal to the state that you defined before. Okay? In literature, you will find the methods where they fix lambda, but this is not very elegant. In general, you should treat this as a parameter that you estimate. So just to give you an idea, because I mean, I told you before that when you write a loss function, you have to make sure that this loss function is efficiently measurable on a quantum device. Otherwise, it's of little use for practical applications. And well, it turns out that also this loss function is measurable. You know, first of all, because the energy here is measurable for the same reasons we were discussing before. But also the overlap part is measurable. So we can see this very, very easily, because if we write this overlap like this, okay, and we unroll, if you want, the unitaries, right? So because we have 0, so here we will have U dagger of theta bar. Again, theta bar are the parameters that I found in the first VQE, and then I have U of theta. Okay. So you see that this has a very nice interpretation because you can interpret this as preparing a state that I will call phi, okay, which is given by, if you want, this part of this ket here. Okay. So this is a state which is obtained by, if you want, acting with U dagger theta 0, U of theta, and then acting on the vacuum 0. So you see that then I have this state, and then what the overlap is, it is nothing but the probability of measuring a string of zeros when I measure in the computational basis this state phi. Okay. So it's just the probability of measuring 0 when preparing and measuring phi. So this state phi, and you see phi is efficiently preparable on a quantum computer because it's just the product, if you want, of two unitaries. So this can be implemented efficiently on a quantum computer. So this means that if you want to estimate this overlap, what you would do, this is one possibility. There are other possibilities that I'm not discussing, but this is what is called typically in jargon the computing uncomputing method. Okay, But in general, so for example, again, schematically, what you do, the drawback of this method is that somehow you have to double the depth of your circuit, because you have to start again with your standard unitary that will have some depth given by this unitary, but then you have to act with the inverse, right? So with this dagger of theta 0. Okay, so you see that if my unitary has a depth of p, then the circuit to measure the overlap will have a depth which is 2p. So this is the drawback if you want this approach. But then, I mean, again, it's straightforward. You just do a measurement here, and you count how many times observe this thing is 0. Okay, so notice that if the overlap is exponentially small, the probability of observing this string of zeros will be exponentially small as well. But again, this is not a problem, because this would mean that in general your state will be already orthogonal to what you are trying to prepare. I mean, to the original state. So there's no loss of efficiency when you use this kind of approach. Yeah. I don't know. Are there questions? I saw something in the chat, but I'm not following. Maybe you can.
Yeah, actually, there are 2 questions.
Okay. Yeah.
I can read them. So first question is there a well-known mapping, or is just proven to such a mapping to exist? Now, I don't know if it's clear written like this. Otherwise, we can ask.
I think this is referring to the combinatorial optimization problems. So if so in this case, I wrote the mapping explicitly. So you see, I did the calculation explicitly. So what was this the question? Yes. Okay. Yeah. So yes. So there are articles where you can find these mappings actually written down. Some of them are very easy to just define, but these are not unique, if that's the question. For example, I could have defined this energy to the power of 4, you know, and this would have given me the same minimum. These mappings are not unique, but in general, you can almost always map all these problems into an Ising model, classical Ising model. Yeah. The other question?
Okay, the second question is, how do we determine the measurability of the loss function?
Yes, so the measurability of the loss function is determined in terms of essentially 2 things. So yeah, this is an important point. So the first one is essentially, am I able to prepare the state, right, that is needed to measure the loss function? Okay, so by construction here, you see, for example, that's why I was writing this as a product of unitaries, because I wanted to show that I can prepare this efficient on a quantum computer. So in general, the rule of thumb is that if you have something which is prepared as a unitary acting on 0, this is efficiently preparable on a quantum computer. I mean, unless the unitary is crazy. But let's say for local unitaries, this is fine. Okay? Now, the other thing that I was mentioning, which is actually as important, is to determine the number of measurements, okay, that you need to estimate your loss function. So in this specific case, I was telling you that the number of measurements that you need will increase only polynomially if you want some epsilon accuracy on your Hamiltonian. But I can devise very easily other cost functions that instead would need an exponentially many number of measurements if you wanted to have epsilon accuracy on the loss function. So in that case, you should discard that cost function, because it means that it is not realistically interesting or measurable on a quantum computer. Okay.
Okay, then actually I see that there is a raised hand. So it's from Maria.
Yeah.
So if you want, you can ask a question by voice. Let's see if it's a mistake, maybe.
Okay, yeah, feel free to interrupt me if you have your questions ready. Otherwise, I will give you the last example of loss function that I wanted to discuss, which is to study to study unitary dynamics. So what does it mean, unitary dynamics? So it means that, you know, until now I've been concerned with studying excited states or ground states, but in general, you know, I want to solve the time-dependent Schrödinger equation, right? So for example, let's say that I have my Hamiltonian and I want to solve, right, for this, and I assume that my Hamiltonian is time independent just for simplicity. And I would like to solve for this, I would like to prepare, if you want, okay, this psi of t. So my task is to prepare now this psi of t, in general, if your Hamiltonian is k-local, it's easy to show that you can do this using only unitaries, so using only gates. However, and this is a very important point in the context of hybrid or NISQ approaches, what you would like to do instead is that instead of using a full, trotter decomposition of your unitary, you would like to use a fixed depth circuit. For example, because your specific superconducting device does not allow you to use too many gates, otherwise you would lose fidelity, as you've seen in the previous talks. So you would like to simulate your dynamics, for example, using a fixed depth circuit, and you would like to do it hopefully also for very long times. Okay, so typically, if you use a trotter decomposition of the unitary evolution, then the number of gates would increase linearly with time. However, if you try to use instead a quantum circuit that is parameterized, we can try to keep, if you want, the depth constant despite the fact that we are using a very long time. So how do we do that? Well, we use we have to use another variational principle, which is known as the time-dependent variational principle. Okay. So this is a method, a principle that is as old as quantum mechanics, essentially. So it's due to Dirac, especially, and Frenkel, who provided a report of this, and also actually in the version that we will use during this, that is mostly used in quantum computing. There's a version of this principle which is very similar, but that is due to McLachlan. Okay, so the main difference is that with this principle we will be working, as I was mentioning, with parameters that are real. Okay, so this is the version that we'll be using during this presentation. So so the main idea is that now what I can do is that I can think that my parameters theta acquire a time dependence. Okay. So I can imagine that my theta, my parameters in the unitary, now will depend on my physical time, if you want, that I'm trying to simulate when I want to prepare this psi. Okay? So what happens then is that I can try to prepare a state psi of theta, so my variational state of t, that will depend on theta, if you want, parametrically through my parameters. Okay? That will be as much as possible an approximation of my exact, if you want, state, which is this psi of t, okay? Instead. So the variational states are indicated because they depend on theta. The exact states are instead do not have any dependence on theta. Okay. I hope this is not too confusing, but this is what I want to do. So I want to find, if you want, a trajectory, right? I want to find how my variational parameters should evolve in time in order to approximate as close as possible at each instant of time my target state that I want to prepare. Okay. So how do I do that? Well, the idea is to define, again, a variational principle that goes as follows. So you know that the exact, so the idea of this variational principle is that we put ourselves at some instant of time, let's say t, and then we look at how the generators of the variational evolution and of the exact evolution will change my states. So what do I mean by that? I mean that, for example, at time t plus delta t, my exact state, right, will evolve, as you know, according. I mean, if I assume that delta t is small, just like this. So I will have my original state, and then I will have my Hamiltonian that again I'm assuming to be time independent that acts on psi of t. Okay, then I will have plus order of delta t squared. This is just the exact evolution that I would have infinitesimally at each time step. However, on the other hand, since the variational state will have a different dynamics that is not, induced by the Hamiltonian, if you want, but is induced by the fact that I'm changing in time my variational parameters. So, for example, in this case, what will happen is that at t plus delta t, my variational parameters in general will be different from what I had at time t. Okay. Again, this is just a matter of Taylor expanding, if you want, the time derivative, the total time derivative of the state. But then you will get delta t times the derivative of my state, my variational state, with respect to my variational parameters theta j, all of them, times the time derivative of my variational state. Okay, and again, plus higher order in delta t. Okay. So you see that I have two words here, two words here. So this is the exact state, the exact time evolved state, and this is the approximate, if you want, the variational state. And you see that I can play, if you want, in order to match these two states at the next time step, I can play with these degrees of freedom. So these are the only degrees of freedom that I can play with. So these are the time derivatives. So this is the, if you want, the slightly different thing with respect to the standard approach of the variational parameter. So I can optimize these time derivatives in order to match these two states. And again, the cost function, in this case, if you want, will depend on this theta dot, if you want, at each time step, okay? Not on theta, so this is again the main difference. And it will just be the, if you want, the overlap between your, if you want, exact state that I've written here, okay? And the approximately evolved time state that I've written here. Okay. I'm not going too much into the detail of how you measure this, but it's a very similar technique, for example, to what we've seen before. So this computing and uncomputing approach. Actually, in the talk I'm giving in the following, I will give you an idea of how we do this in practical applications. Okay, but in general, you see that again we have a loss function that depends now on the theta dot. So if you want on the variation in the parameters that we have to do at each time step. And we can use the quantum computer also to measure this loss function to minimize it, so to find the optimal change in the variational parameters. And then at each time step, we can, if you want to reconstruct a trajectory of variational state of variational parameters that best reproduces my dynamics. Okay, so this is the approach that I will also discuss also in my, if you want more research talk in the following. Okay, so maybe I guess it's a good time to do a break if you agree.
Yeah. Before going for a break, there is a question. Maybe we can answer now. So the question is: do we expect that QAOA to be more efficient than the quantum annealing for combinatorial optimization, or we still don't know that?
Okay, that's a good question. Thank you. So again. If a problem is NP-hard, so for example, this, let's say this set partitioning or any trivial enhancement, it will stay NP-hard also as far as we know on the quantum computer, okay? So there is no exponential speed up, I mean, there's no, sorry, exponential to polynomial reduction that is known to the humankind for these optimization problems, even if we use a quantum computer, okay? Now, the question is this going to be more efficient than a classical approach? The evidence that we have so far is that not really. Again, it's also true that the kind of hardware we've been experimenting with is not, very big. So there might be more specific cases where we also have better hardware, larger hardware. We devise also better variational approaches in the quantum setting that will allow us maybe one day to have also competitive or better even the classical optimization approaches. Yeah. But at the moment, no. Yeah. Okay, thank you. So I suggest that if you don't mind, we do only 5 minutes of break. Otherwise, I will not finish on time. So we'll come back around 10:06 or 10:07. Thank you. Okay, welcome back. Are there more? Okay, yeah, okay. There are no more questions. Okay, now I will now discuss another important ingredient. So the first ingredient that we were discussing, that I was discussing, are the loss functions, because essentially they define the problem that you want to solve. Okay. Then the second ingredient in the list that I was showing at the beginning are the parameterized quantum circuit. Okay, maybe as SWOT, but in any case, so the second ingredient that I will discuss now are parameterized quantum circuits. So what do I mean? What I mean here is that for these things to be practical, we also need to have a family, if you want, of circuits that make sense for the problem that we want to solve, right? So I haven't told you too much about how do we pick, for example, these unitaries, U theta, and how they are typically chosen to solve some problem, or to try to solve one problem. So for concreteness, I will focus only on the case of ground state. So when I try to prepare the ground state of Hamiltonian, but I mean, some of these considerations can also be generalized to the other problems. So I mean, one of the ideas that are in the field that I think it's pretty influential, and it's very interesting, it's to consider actually a family of circuits that is inspired by an algorithm that we know works when to prepare the ground state. Okay, so an algorithm that we know in principle works to prepare the ground state. So ground state preparation is the adiabatic state preparation method. Okay. So our idea now is that we look at how this approach that we know works in principle to prepare the ground state, and we try to imitate it as much as possible, to mimic it as much as possible with a parameterized instead circuit. Okay. So what is the adiabatic state preparation approach? Maybe you've heard about it, but just let me quickly recap. So essentially, again, my goal is to prepare the ground state of some Hamiltonian H, that now I will call HF, H final, for reasons that will be clear in a moment. But I assume that instead I'm able, because you know, I know how to do that, I'm instead able to prepare the ground state of some, let's say, H0 Hamiltonian, that is called sometimes the deriving Hamiltonian. For example, H0 can be an easy Hamiltonian that for which I know to prepare the ground state exactly and efficiently. So for with, I don't know, just one layer of gates. And then the idea of the adiabatic approach is that I define a time-dependent, this time Hamiltonian, which is essentially an interpolation of these two terms. So the first one, which is H0, and another one, which is this final or target Hamiltonian that I want to, whose ground state I want to prepare. So you see that the way I've written this interpolation is that the Hamiltonian at time t equals 0 coincide with this simple Hamiltonian H0, and the Hamiltonian at time tf, or you know, the final time or the adiabatic time, I don't know how you want to call it, is instead equal exactly to the final Hamiltonian I want to do. Okay. Now it turns out that if I do unitary evolution with this Hamiltonian, and I do this evolution slowly, so slowly means that that I take this time much larger than the gap, okay? The minimum gap that I find in this time evolution squared, inverse of this gap squared during of this Hamiltonian. Okay, so h of t is a Hamiltonian. At each time, it's a parametric Hamiltonian, depends on t, and each time it will have some gap between the ground state and its excited state, right? So this gap will depend on time in general, right? So if I call this gap delta of t, then the adiabatic theorem of quantum mechanics tells you that if Tf is much larger than this time scale, then at each instant of time I will be in the ground state of this h of t, So if I follow this evolution up to TF, then I will stay by definition in the ground state of my final Hamiltonian, which is HF. Okay? So in principle, you see that this is a protocol well defined to prepare the ground state using only unitary evolution. Okay. Now the problem, of course, again, there's no free lunch, is that in general this approach will break typically because the gap will go to zero at interesting points during the dynamics, or will be exponentially small. So in general, again, we don't have any polynomial time approach to prepare the ground state of a Hamiltonian, even on a quantum computer. Okay, so if sometimes you hear that you can prepare the ground state of Hamiltonian on a quantum computer efficiently, this is false. Okay, so there is no known quantum approach that can do this in polynomial time. So just to make it clear, we have some speed up, of course, but again, for example, you see it here that the gap typically will go to zero and the time will go to exponentially. So you have to run your computer exponentially long. Okay, so this is the adiabatic state preparation approach. So this defines a well-defined unitary dynamics. So what we can try is that we can try to copy it, to mimic it with our parameterized quantum circuit, possibly trying to have a total propagation time which is shorter than the original TF that might be too large. Okay, so what does this mean? Well, just to be concrete now, let's assume that I can write my Hamiltonian at each time as the sum of m terms, time-dependent terms. And the only thing that I'm assuming here is that these HS terms do not commute in general. Okay, so I'm just dividing, if you want, the terms in my Hamiltonian in a way that do not commute, grouping them in a way that they do not commute with each other. S and S prime will not commute even at the same time. Okay. Now, then you know that if I want to study if I want to implement the unitary dynamics induced by this adiabatic state preparation approach on a quantum computer, I will need first of all to define a small time step delta t. Okay. And if you want to divide this time evolution into small time steps pieces for some, so up to some total number of pieces that is of order t over delta t, so delta t is my time step, and then I have the exponential of minus I delta t, the Hamiltonian at this time step p delta t, okay? Acting on my initial state. I've just split my time evolution into small delta t pieces. In this small delta t, I can assume that my Hamiltonian is constant in time, so I can just do the standard unitary evolution. And then what I can do is that I can trotterize this time evolution using, if you want, this decomposition in terms of S, in these M terms that I showed before. So this will be the product over P, again, as I wrote before. And then I will have the exponential minus delta t. Then I will have my first term, which is h1, again, computed this time, p delta t. The second time, okay. The second term, sorry, h2. Okay. And all of these will act on my initial state. So you see that I've defined now a sequence of unitaries, a lot of these unitaries, because, again, the total time may be very long. But in principle, I can apply each of these unitaries efficiently as a gate on my initial state. Okay, so just to give you a simple idea. For example, if I have again, if my goal is to prepare the ground state of the transverse field Ising model, then what I can do is that I can define my h of t, my Hamiltonian, to be the sum of a first term that will be my driving, if you want, term that I will define, that was defined before, which will be just the term which is proportional to sigma x. Okay, so the term that I called before sum of I sigma I of x. Okay, and then now I can define my instead yes. So this would be my driving term, and then the final Hamiltonian will be just just my transverse field Ising model Hamiltonian. Okay. Now, if you group everything together, you can immediately see that then my time-dependent Hamiltonian that I want to simulate now will have the form of this driving term. this sigma x term plus this T over TF sigma z term. Okay. So in other words, what I'm doing is that at time t equals 0, when this term here is 0, I'm just preparing the ground state of this term that I can do efficiently. It's just a bunch of Hadamard gates, because this is just the ground state of this term will be just all the spins aligned in the x direction. And then what I can do is that I can turn on slowly this interaction term with this rate. Then at time tf, then I will have all my Hamiltonian, which is the transfer. Okay. Now you can, as you know, you can trotterize these, because if you consider, for example, h1 to be sigma 1 x, h2 sigma 2x, etc. So all these local terms that appear in this Hamiltonian. I'm sure that you've seen this before, also during these lectures. But in practice, you will end up with an ansatz. So with a sequence of unitaries that realizes this time evolution in this adiabatic state preparation approach, which essentially, for example, for 4 qubits would be the following. So you apply a bunch of Hadamards at the beginning, okay? So these will just prepare the ground state, if you want, of my state at time t equals 0. Okay, you can show that easily. Then what you do is that you apply, for example, some, let's say that I have interactions RZ, along across these 2 qubits. Then you have to apply a rotation RZZ, whose angle will depend on delta t. Okay, I'm not writing it explicitly, but it would be something like delta t times something. Okay? And then you have another, I don't know, another interaction term here. Again, another ZZ term. Okay, and then I don't know, you might have another ZZ term that entangles these 2 qubits. Why not? Okay. And then, I mean, you have to apply, you have to act with this instead with the driving third part in the Trotter decomposition, which are these Rx term. Okay, so here again, I'm using standard notation that you should have already seen, but RZZ of an angle theta is just e to the minus a over theta over 2, let's say sigma z on qubit I, sigma z on qubit j, for example, with an angle theta, or Rx is the same, but only for my sigma x. Okay. So again, you can write your trotterized Hamiltonian just using these 2 gates where the angles theta are fixed and are given by simply some functions that I'm not writing down because they're a bit, you know, not very nice, but they will depend, you know, exactly on just on delta t and the instant of time. And then you have to replicate, if you want, this part of the circuit many times of the order, so a number of times that is of the order of TF. Okay. Now, then the idea of these parametrized circuits, sorry, is to take this form, essentially exactly this parametric form. So this structure of the circuit, where I have this rotation on Z along ZZ, and these are X rotations, and instead of fixing the angles, I make them free. Okay. So the idea is that I will just have now my general rotations to be, you know, some parameters that I can change, and that will depend on some parameter theta that I can change as much as I want. Okay? So both in the sigma x direction or in the ZZ direction as before. So this is the main idea, if you want, of this QoA-like or in general adiabatic inspired ansatz to prepare the ground state. So the idea is that you take the standard ansatz and you parameterize the gates. Right? So this the hope is that by doing that you will be able to prepare the ground state using a much smaller depth than what you would need in the standard case. There is another important family of parameterized circuits, which are the so-called hardware efficient. States, parameterized states. And this is one of the main reasons why also these variational states are useful for near-term approaches, because what you can do is that, okay, you say, I have a small quantum computer, it's noisy, I can only run 4 gates, hopefully more than 4, but I can only run 20 gates. These gates take a specific form. I can just then try to use this specific form of the gates that my hardware implements that can natively do. And then I can try just to leverage as much as possible what the hardware is offering me to prepare my target state. Okay. So, for example, one typical ansatz that people use, again, given the constraint of the hardware, is to take something where you have let's say some, where you have some unitaries UK that depend on some parameters, but you also have some other unitaries that do not depend on any parameters. So typically what happens is that on hardware you can, for example, implement 2 qubit gates that not always are easy to parameterize. For example, if you can implement easily a C0 gate that does not contain any rotation angle. And these typically are also found at some specific positions, or they connect to specific qubits or some specific geometry for the qubits. So you just keep those as they are given by the topology of your hardware. But then what you can do, however, is to try to optimize just these that typically are just single qubit rotations. So this is, you see, a much more restricted ansatz that you are using. However, you know, it's hardware efficient. It will run natively on your hardware, and it will be essentially the best ansatz that is suited for your specific hardware. It will depend, of course, on the geometry. It might not give you the best results in terms of accuracy, but still might be a very good ansatz for what your hardware is giving to offer. Okay. Okay, so I just gave you 2 very simple, 2 examples of kind of answers that you can use in this context. I would say that the first one is one of the most used the states that typically are encountered when you try to prepare the ground state. There are more specific ansatz states that are used for quantum chemistry. I believe that this will be discussed also in the talk by Ivano later today. But in general, again, the idea is that if you know an algorithm that prepares your ground state, even though it's not efficient, you can try to write down the structure of the gates, and then you can try to parameterize these gates instead of having them fixed as for the original, possibly inefficient approach. And this reasoning can be done also for other, if you want to state preparation algorithms that are also, for example, true in the case of dynamics. Now, the last topic that I wanted to tell you about, that is somehow if you want to finish this discussion about hybrid approaches, is the third ingredient that I wrote on my list, which is about optimization, right? Because, you know, we've been discussing about the loss function, we've been discussing about the ansatz, but we still don't know how to optimize this thing, right? So I told you that we want to find the minimum of these energies or of the other loss functions. So in general, I mean, again, I will restrict my attention here to a simple case where I have my state, which is parameterized by, again, a sequence of unitaries, UL of theta L up to U2 of theta 2, U1 of theta 1 that act on the vacuum. And again, I will restrict my attention to the case of loss functions, like for the energy, that are expectation values of Hermitian operators B. Okay. So these are the 2 assumptions that I'm doing. I'm taking also the parameters to be real. Again, Then what you do, one very common approach that you can do is that you can just do a gradient descent optimization. Which is very, very easily written down. So essentially, this is an iterative approach. So I imagine that I am at iteration I. So this is the iteration index, if you want, for this optimization approach. Then what I do is that I can, the first step is to measure the loss function on the quantum hardware. Okay. With the current choice of my variational parameters, theta I. So I imagine that at step t, at step I, my variational parameters take some value that I call theta I. I go on the quantum computer, I measure the loss function, L of theta I, but I also estimate the gradient of the loss function. So that, let me call it G of K. For this, again, specific choice of the parameters, that is just, for example, one component will be the derivative of the loss function with respect to parameter theta K. Okay, so I can estimate, and I will tell you in a moment how to do that on a quantum computer, the gradient. Then with this information, so both the loss and the gradient, I can go back to the classical computer and I can tell the classical computer, listen, I just want to update my parameters. So the simplest way that the classical computer can do that is, this gradient descent or stochastic gradient descent in this case, where at the next step, so at step iteration I plus 1, my parameter K is just the parameter I minus a small coefficient, eta, which is called the learning rate in the jargon of machine learning, times the component of the gradient. Okay, so you see that I'm trying to follow the direction of the gradient descent, and eta, which again is called the learning rate, is a small parameter that I should positive, that should be small enough to guarantee that this procedure converges. And then 3, I mean, of course, I will quit this loop when converged. Converged means that the gradient, for example, of my loss function will be 0, I mean, or essentially as close as 0 as possible in this optimization procedure. Okay, so this is standard if you want gradient descent. It's not necessarily, as I will tell you also more about in the next talk, the most efficient way of optimizing the parameters, but it's still the most straightforward way you can. Now, there is an important ingredient. Again, the thing that you have to ask yourself when you implement these approaches is how efficient are these approaches, okay? So how efficient it is to run all of these using quantum hardware? What are the requirements on the quantum hardware? Can I run this, again, seamlessly, or do I have to do some improper assumptions on the number of measurements, for example, that I need on the quantum hardware? Well, as you can see here, the ingredients that I need are essentially just the loss function and the gradient. So for the loss function, I've already discussed before how we do that. So how we measure it efficiently using just samples. But for the gradient, I haven't told you how to do that. So this is also a quite important topic, if you want, in the field. There is actually, it turns out that there's an efficient way of measuring the gradient of your quantum circuit using just efficiently realizable operations on the quantum hardware. And the family of approaches that does that is known in literature as the parameter shift rule. Which again is just a way of, it's just the name of the rule or the name of the method, as I will show you in a moment, used to find an efficient estimator, if you want, of the gradient. So for simplicity, I will restrict myself to unitaries that have the form of a rotation. Okay, so these are very common, but I will make the extra assumption that the operator, the rotation operator, if you want, so the Hermitian operator Sk that appear here, has the property that it is involutory. So it means that the square of this operator should be equal to the identity. Okay. So I'm just taking, if you want, parameterized unitaries with this property where the generating operator of the unitary is involutory. So this is called involutory. So you might wonder if this assumption is too restrictive. Actually, it's really not, because essentially all the Pauli matrices, as you know, satisfy this property. So for example, if you take Sk in the set, I don't know, sigma x, sigma y, sigma z, okay? You know by definition that sigma, all the squares of the Pauli matrix is equal to 1. So this is clearly verified for those. Not only, this is true also for 2-qubit or n-qubit gates for what it matters. For example, provided that these are, for example, taken as products of Pauli matrices on different qubits. So, for example, I can take sigma x I on qubit I, sigma xj on qubit j. You see that still the square of this operator would be equal to 1 by definition. Or I could take, I don't know, sigma yi, sigma z, j, whatever you want, essentially. Okay. So this is actually a very general family of very general class of unitaries. There are some that are not in this family, but that you can either decompose in the gates of this form, or you can use other approaches, but that I will not discuss. So by far, this is, you know, one of the most interesting class of unitaries that we want to deal with. Now, why am I doing this assumption of being involutory? Well, because it turns out that involutory matrices have a very nice property. So, for example, if you write down the unitary explicitly, okay. So if you do a Taylor expansion, if you want, of this unitary, you will have the identity, and then you will have Sk, theta k over 2. Then you will have minus 1 over 2 factorial, Sk squared. Theta k over 2 squared, okay, plus, okay, I'm just writing the last term, 3 factorial Sk cube, and then you have theta k over 2 cube, okay, and all I'm just writing a few terms in the Taylor expansion. Why am I doing that? Because again, I know now that S squared, for example, is equal to the identity. So this means that all the terms that are of higher power than 1 will essentially disappear or will be actually reabsorbed in lower orders in S. So either 0 order or order 1 in S. And at the end, if you resum essentially these two series, you get that this will be equal to the cosine of theta k over 2 proportional to the identity. So everything that is proportional to the identity will stay there. Minus I, the sine of the same angle, theta k over 2, times Sk. Okay, so you see that this is a very important property, because I can do this unitary, if you want, explicitly, and it will be linear at most in this imaginary operator Sk. Okay. Now, this is the first property that we will need. The second property that we will need is what happens when you do the unitary conjugation of an arbitrary operator with this unitary rotation. So what does it mean? So it means that if I take some operator k and I do its unitary conjugation, so meaning that I multiply it by u dagger, you know, I do if you want, a rotation in this basis. So I take some arbitrary operator k, okay, and then I rotate it with this u. Then you can show, I'm not showing it explicitly, but it's a very simple calculation, that this will be written in general as some operator A plus B, times the cosine of theta k plus C, another operator, the sine of theta k. Okay, so the very important point is that these operators A, B, and C, right, do not depend on theta. You can show this with one line of calculations. I'm not doing it, So this in general will depend, of course, on K and on S, A, B, and C, but they will not depend on theta. So the only parametric dependence that you have on theta is in, if you want, coupled with this cosine and sine term that are the proportional to these two operators B and C. Okay. Now, why this is important? So this was, if you want, the property 2 that I was telling you about. It's important because there is also a property 3 that comes out of this, which is immediately the consequence of the fact that when you of the form that the derivative with respect to theta k of this unitary conjugated operator takes. So if you just do the derivative of the expression that I wrote before, you have a sinus term, which is b minus b theta k, plus c, the cosine of theta k. I just took the derivative. But you see immediately that I can also write this as this unitary operator k rotated, but with a theta k plus pi over 2 minus the same operator rotated with theta k minus pi over 2 over 2. So why? I mean, you can see it immediately. So you see that in the gradient I have minus sine and plus cosine, whereas in the k I have plus cosine and plus sine. So if I send theta k plus pi over 2, this becomes a minus sine and this becomes a cosine. Okay. If I do the same with minus, I will get minus pi over 2. I will get the opposite signs. But if I take a linear combination of the two, you see that this term a cancels. Okay, and then I end up with the derivative that I wanted to find. So this is a very important result, because now it will allow me to write an efficient way of estimating the gradients. See, this was result 3, because if I write now the gradient, so the derivative of my loss function L with respect to I don't know, my parameter theta k, okay, then if I write this explicitly, okay, so sorry, just a second. I forgot to introduce the quantity that will be useful to simplify this notation. So the quantity that I wanted to introduce is the following. So I will define now, I will write my general unitary u of theta as some other unitary v of k that will depend on all the parameters but theta k. Okay. Then my unitary u of k that depends on theta k, and also another unitary wk that depends on all the, okay, actually a better way of writing this is this will depend on all the theta k that are larger than k, and this will be on all the theta k that are smaller than k. Okay. It's simply, I'm simply saying that I'm taking my unitary that I wrote here at the beginning. Okay, I'm taking a UK here in the middle, and this part here will be my V operator, and this other part here will be my W operator. This is just for notational convenience. Okay, and if I do that, then I can easily see that the derivative of my loss function can be written as something that I define to be psi k times then u dagger k theta k in operator qk times uk theta k, and again psi k. Okay, where I've defined this psi k to be just the action of this on zero of this wk operator that I defined above. Okay, and the qk instead is just the conjugate, if you want, of my operator b that I wanted to measure in this way with this operator v. Okay. Now you see that I'm in the shape of using exactly the result that I introduced before, that I derived before, because you see that this qk, okay, is now conjugated between u dagger k and uk. So it's exactly of this form that I wrote here. So I can efficiently write this derivative using this form that I introduced here. Okay. So if you do that, I mean, it's just now a matter of rewriting everything. You can immediately see that this will lead you to an expression which is the following. So you will have psi I, you will have your unitary UK computed on theta k plus pi over 2 dagger, your operator qk that I define here, UK theta k plus pi over 2, psi k, psi k, and then you will have minus, okay, the same expression but with a minus pi over 2, and then you will have a 1/2. Okay? And then when you put everything together, you can just beautifully rewrite this gradient as the difference of two loss functions. So it will be the loss function computed at theta 1, theta k plus pi over 2, and all the other parameters are unchanged, minus the same loss function computed theta 1, theta k minus pi over 2, all the other parameters unchanged, divided by 2. Okay, you see that this comes from the fact that if I shift, you see, this parameter by pi over 2, both on the left and on the right, I'm just redefining my ansatz in a way that only the parameter theta k is shifted by pi over 2, or by plus pi over 2, or by minus pi over 2 in this other term. And this is very important now because it's telling me that the kth component of my gradient is found just, again, efficiently as the difference of two loss functions that I again compute efficiently again on my quantum computer. The only thing that I have to do is that if I want the kth component, I have to first compute it by shifting one of the parameters by pi over 2, and then shifting another time but by minus pi over 2. So this will give you immediately an efficient way of computing also the gradient, and then using it to estimate, to do your gradient descent operation. Okay. Okay, so this was essentially the last thing I wanted to tell you today. There are many other research directions. So one that I didn't have the time to cover are the so-called barren plateaus. Which is the consideration that enters the theoretical consideration that enters this optimization problem. So essentially, it turns out that there are cases where your circuit is untrainable, so you cannot optimize it, even though the loss function in principle is measurable. So this happens, for example, if the gradient, so if the magnitude of your gradient is exponentially small. So if your gradient is exponentially small, this means that you cannot really do much progress in your optimization. And you can show that this happens if you start essentially with random parameters in a general circuit. In general, this would be the case. So in the first iteration, your gradient will be exponentially small, so you will not do much progress. So typically, there are ways of circumventing this issue that is not addressable in general. So an efficient way of doing this, I mean, a good way of doing this is, for example, to just initialize your parameters in a regime which is not random, but it is instead, for example, inspired by physics, for example, by this QA approach. Or in other cases, it's known that if you change a bit your loss function, these barren plateaus can disappear if your circuit is not too deep. But again, this is really a matter of research. I don't want to enter too much into the details. I just want to tell you that while it's true that this is an important issue, it's also true that we have several ways of circumventing it that work typically fairly well in most applications. Okay, so thank you for your attention. It's been quite a journey, and there will be also another talk now. Again, if you have questions, maybe I will take them now for a few minutes, and then we will go to the talk. Thank you.
Thank you for being also perfectly on time. And yeah, who has questions about theory can ask. Actually, since I don't see question for now, I give time to them. I wanted to ask a question. So I wanted to know if there is some work going on that exploits, let's say, systematically the symmetry of a system to generate an answer that can be particularly efficient.
Yes, so I wouldn't say yes. So there is some. Yeah, for example, I mean, if you take this QoA inspired or this adiabatic ansatz, so you see that if you use you know, a reasonable driving Hamiltonian that does not break the symmetries of your final Hamiltonian, then the resulting circuit that you have here will exactly have all the symmetries of your, for example, the translational symmetry of your Hamiltonian. So I would say that again, yeah, this is a good way if you want to systematically include also some of the most important symmetries. However, it's also true that it's in some cases it's best to break the symmetries and then this is known both classically and also I would say in quantum circuits, and then somehow build them up at the end of your calculation. So there's been some work in this direction. We're also exploring some in this direction. It's very, very interesting. Yes, so in that case, you will need to devise some modification of the VQE to represent the symmetries at the end of your simulation. Not directly into the ansatz. But yes, yeah. So these are the two approaches. I would say either you build an ansatz which already has the symmetries like this one, or you represent the symmetries at the end.
Okay, thanks. So I see no other question. I think that the theoretical part was pretty clear, so thanks. And I guess there will be many more questions about the research that is very interesting. So I would say we can have this 10 minutes break. We'll be back at 11 with the lecture.
Thank you very much, Stuart.
Thanks.